want to find absolute maximum and minimum values of a function. Back in Calculus 1, you had a function y equal f of x defined on a closed interval AB. We were guaranteed that there would be an absolute maximum and an absolute minimum when that interval was closed. The way we found it was we first found the critical points in the interval AB. So let's say that x equals c is a critical point in the interval AB. Then we looked at x equal a and x equal b and calculated the actual y value at each of those values of x. Whichever led to the largest y value was our absolute maximum. So the largest y value of the critical points or the endpoints gave you the absolute maximum, and the x value that led to that absolute maximum was where it occurred. Likewise, the very smallest y value of those x values was the absolute minimum. So you get the absolute maximum minimum by looking at critical points and the endpoints of the interval. So now we don't have an interval, we now have a closed region. So f will be continuous on a closed bounded set. Now f will have an absolute maximum at AB if f of AB is greater than or equal to f of xy for any other xy in the domain. F will have an absolute minimum at AB if f of AB is less than or equal to f of xy for all other xy in the domain. Now to find the absolute maximum and minimum, we have that f is continuous on a closed bounded set. We get the absolute maximum minimum by looking at the critical points and looking at the boundary and determining the values that where f is the largest at either the critical points or on the boundaries of f. So we'll have to identify the points on the boundary that would lead to the largest values and the smallest values, and find the critical points and find which of those lead to the smallest and largest y value or z values. So that will be how we'll find the absolute maximum and minimums. Look at the critical points for the open set, and then look at the boundary points, and then just figure which gives you the very largest z values and which gives you the smallest z values. Okay, so now let's find the absolute maximum and minimum values on this curve. Now first, we'll find the critical points and get the possible maximum and minimum values, the local maximum and minimum values inside the set, the domain. Now notice the domain is the set of all points on the circle with radius 2 and inside the circle with radius 2. So first, let's find the local maximum minimums inside that set x squared plus y squared less than 4. So we'll do that by using the second derivative test. Get the partial derivatives. F sub x will be 2x minus 2. F sub y will be 2y plus 2. And these both will be 0 when x is 1 and y is negative 1. So the only critical point is the point 1, negative 1. And the function value at that point (1 plus 1 minus 2 plus 5, which is 3. So that's the y value, the z value at the point 1, negative 1. Okay, so now we've got the critical points and we found our local maximum or minimum inside the set. Now let's look at the boundary. Now to look at the boundary, what we're going to do is to change this equation, the function, into a function with one variable. Then we can find absolute maximums and minimums. So we can do that by looking at the fact that this boundary can be defined parametrically. So we're taking a boundary that's defined right now with two variables x and y, and we can define it with one variable using a parameter. So I'm going to define the boundary as x equal to 2 cosine of theta and y equal to 2 sine of theta. And that just defines that circle of radius 2 using one parameter. And theta will go from 0 to 2 pi to create that circle of radius 2. So now, I have values for x in terms of theta and y in terms of theta. So I'm going to rewrite this function then in terms of just theta. So this function f of xy becomes the function just in terms of theta. So I'm going to call it g of theta equal expanding combining the first two terms and factoring out of 4, you have 4 times sine squared plus cosine squared, which if you remember your trig identities, in parentheses is just a 1. So g of theta is equal to 9 minus 4 cosine theta plus 4 sine of theta. Now, this is the function that has the same values as the function f, but in terms of one variable. So we've parameterized that curve along the surface of f. Okay, so now let's find the maximum or minimum values of this function. So now that it's just one variable, we can get that by just taking the derivative and finding the critical points. So g prime of theta will be 4 sine of theta, derivative of cosine is negative sine, plus 4 cosine of theta, and we set that equal to 0. So that means that sine of theta plus cosine theta is equal to 1, or sine theta is equal to negative cosine of theta. I'm going to divide both sides by cosine of theta. And so I'll have sine theta over cosine theta equal negative 1, or just tangent of theta equal to negative 1. Now the values of theta for which tangent is negative 1 would be quadrant 3. The reference angle is going to be pi over 4, so 3 pi over 4 and 7 pi over 4, or negative pi over 4. Okay, so quadrants 1 and 2 and 4 is where tangent's negative. Okay, so that's the values of theta that would lead to the maximum or minimum values. And let's find the points that would correspond to that. So the points x, y, I'll put 3 pi over 4 in for theta into the parametric equations here. So cosine of 3 pi over 4 will be negative the square root of 2 over 2. So that'll be negative the square root of 2. And then sine of 3 pi over 4 is positive square root of 2 over 2. So that'll be square root of 2. And then when theta is 7 pi over 4, cosine will be positive, so it'll be the square root of 2, and sine will be negative, so that's negative square root of 2. Now we don't really need to worry about the derivative test. These are the critical points, so these are where they will occur if there is a maximum minimum. So now let's just check our z values of the function at these points. So f of negative the square root of 2, square root of 2, comes out to be 9 plus 4 times the square root of 2, which is approximately 14.7. And f of square root of 2 negative square root of 2 comes out to be 9 minus 4 times the square root of 2, which is approximately 3.3. So, comparing the z values for all three of these lead us to the absolute minimum value of f is 3, and that's occurring at the point 1, negative 1. And the absolute maximum value of the function f will be 14.7, or 9 plus 4 times the square root of 2, approximately 14.7, and that occurs at negative the square root of 2, square root of 2. So now let's look at that graphically. Okay, so what's going on here? This is the graph of the surface. It's this paraboloid. We have a constraint given by the set R. That's our domain of the function. And we're looking at the circle of radius 2 and everything inside. So what we found is that at the point 1, negative 1, we actually have the smallest possible z value of 3, and that is the lowest point on the paraboloid. So that's our absolute minimum. When we looked at the boundary, we found two possible points. One here was where the angle was at 3 pi over 4. So we were looking at this point right here, negative the square root of 2, comma square root of 2, and it corresponded to this point on the surface that gave us that 9 plus 4 times the square root of 2, or approximately 14.7. And the other point on the boundary, see, as we're going around this circle, you're moving along this path on the surface, and the lowest point along that border of the circle was at this other point over here, and that was the 9 minus 4 times the square root of 2, which was approximately 3.3. So you can see it's a little bit higher than that very lowest point, which occurred at a point inside of the circle. So the local maximum occurred at 1, negative 1, and that really was the absolute maximum, minimum as well. And then the absolute maximum occurred on the border, and that was at the point negative square root of 2, comma square root of 2. Now let me show you another way to look at this, and this is what we're going to get into in the next section. Looking at some of the level curves, the smallest level curve for which there's, an intersection with this paraboloid would be where the z value was 3. So here's our z value of 3 level curve. So now let z equal 4, 5, 6, and get the level curves. And notice they're all concentric circles here. So the level curves are in green. And that point in the middle of that innermost circle is where the actual absolute minimum occurred. And notice that where that constraint, see, the green circles here are all the level curves. But now in blue in this diagram is our constraint. So the blue here is the constraint, which is the circle x squared plus y squared equal to 4, the circle with radius 2. So now look at where the constraint intersects the level curves. The smallest level curve that constraint intersects is right here. And that gives us that lowest z value for the region inside of that circle. And now look at the biggest level curve, which is the furthest one out here. That's the biggest z value that the constraint has at the same time that the region x squared plus y squared, the boundary of that has a level curve for. So this point here is where the constraint intersects the largest level curve, and that's where we have our absolute maximum at. And where the constraint intersects the smallest level curve, for the smallest z value, is our absolute minimum. So in the next section, we'll look at where the constraints actually intersect those level curves to determine where those absolute and absolute maximums and minimums occur. Now again, this problem, we actually had a closed domain. We were looking at a constraint in a boundary condition. So we could look inside to get our absolute, the local maximum minimums, and then we looked at the points on the boundary to determine which ones gave us the absolute maximum minimum values of the function.